Good afternoon. This is the class of this is the class of Tele 1022 25 fall term 2025 fall telecommunications, Fanshawe College, London, Ontario. All right, it's the last lecture for this term, and we're going to expand on the last lecture that we had. We're going to expand on, let's see here if the effects work. Whoa. The PCM, pulse code modulation. We're going to expand a little bit on sampling rate and aliasing, quantization, encoding, and quantization error. And we're going to cover some noise. If you don't have a good coffee yet, then maybe well, I got one coffee here, so I'm going to sip on it as we go along. All right. So let's get this show on the road here. All right, sampling. As far as digital sampling, excuse me. What did I write here? Sampling is measuring the amplitude of incoming analog wave at regular intervals. That's basically if you want to close this idea in one sentence, that would be it. All right. But then, of course, we can expand on that, elaborate a little bit on this thing. Now, sampling rate. There are certain things we have to talk about when it comes to sampling. Sampling rate defines how often the samples are taken. And it can be measured in hertz, or it can be measured in samples per second, which comes up to the same thing in this case. Now, here we have a little bit of a graphic example of what I'm talking about. Here's the input signal. Three types of input signal. We've got a straight line, we got a triangle wave, and a sine wave. And that here is the time of the sampling time. There will be sampling interval. Right? And this will be the sampling frequency. Now, you can chop it into finer chops, or you can sample, you could divide that signal in order to reconstruct that in not so fine chops or pieces, depending on what you want to accomplish. Do you want to accomplish just the voice communication? Then you don't have to chop it as fine. Or if you want to establish a fine or high fidelity kind of an audio, then of course you have to chop the signal into many, many more pieces. And so you could reconstruct that as as close as possible to the original analog audio signal. Now, the digital sampling in the past was stumbling a little bit as the technology was developing. And now, at this point, considering the technology that's available and the technology that's available to our or to us as I call regular bread eaters, it is has gone long way since I would say 20, 25 years ago, to the point that you can assemble pretty good, if you want, a recording studio at your own home, spending a fraction of what had to be spent years ago on this. Years ago, you would probably have to sell your house to buy this equipment, and now you can just spend $2,000-3,000, maybe up to $5,000, and you can have pretty nifty recording studio with high fidelity audio recording and manipulating and processing and all that. So over here we got the triangle wave. Of course, see we have chopped that triangle wave into different pieces, and we can just connect the dots and reconstruct almost as it is. If you chop it in finer pieces, you're going to get more true representation of what went into the system. So when we talk about this, we have two things to consider, right? Let's say, well, let's get this triangle wave here on the screen. Um, how fine or how exact the final outcome is going to be. I'm talking about the reconstructed wave on the output or modulated and demodulated signal depends on basically, for the most part, basically two things. How fine you're going to chop this time wise, how often you're going to take a sample of that. So be sampling frequency or sampling rate. And you're going to also, it also depends on the resolution of things, on when you take the signal from its minimum to the maximum, how fine you're going to chop it vertically as well. What is the smallest difference that you're going to register in order to reconstruct? So we're chopping the signal this way and we're chopping the signal that way. And that basically defines on how fine are we going to reconstruct or demodulate the signal. We talked about the Nyquist or Nyquist-Shannon theorem, and which, as a review, it says to accurately reconstruct frequency of the sinusoidal or continuous signal, the sampling rate, which is how often we take the sample, must be at least twice the highest frequency of the signal. This way, as you remember from the previous presentation, we can actually reconstruct the frequency of the wave. Now take a look at this here. Human hearing range is 20 hertz to 20 kilohertz, 20,000 hertz, officially, right? Now, some of us can hear up to 20,000 hertz. Some of us can't. And most of us can't in this sort of virtual room, can say that. Because as we age, we begin to lose the higher end, and we're going to hear less and less from the top of the spectrum that we're presented with, which is 20 kilohertz. So using the Nyquist idea here, Nyquist-Shannon theorem, the highest frequency that we can hear is 20 kilohertz. So multiply that, you're going to have 40 kilohertz. And take that a little bit higher just to make sure that we can reconstruct all the thing that we can hear. Then we can take it to 44.1 kilohertz, and that is actually the CD quality sound. All right, now 48 kilohertz is a DVD, and high resolution audio would be 96 kilohertz or even 192 kilohertz. So that's pretty high sampling rate. That's way beyond what we can hear, but it actually helps with some of the processing of the signal before it's being served to you. Now you can see that just following the Nyquist theorem, as far as we remember, we can reconstruct the frequency of the signal if we sample that at twice as quickly, all right, as the frequency is. That doesn't let us reconstruct the shape. However, if we just take a look at or consider what constructs the sound wave, the music that we hear or whatnot in high fidelity, which is up to 20 kilohertz, those highest frequencies would be the harmonics that compose the final shape. So we don't need to know we need to know the frequencies of those. We don't necessarily need to wonder. Um, we don't need to necessarily wonder about the shape of that waveform because we know they're going to be sine waves because those sine waves will be the harmonics and in their simplest form to construct the shape of the main signal. So twice as high as the highest frequency that we can hear is okay for us to actually have something that we can consider hi-fi or high fidelity audio for the CD quality. The other thing we have to make sure that here's that equal or greater sign for the sampling frequency, how quickly we can how fast we can sample those. It should be slightly higher because there is that possibility if we do exactly half, then if by some coincidence we start sampling, well, not from somewhere within the waveform, but we start sampling right at the half of the frequency, we're going to sample a bunch of zeros. Not likely to happen, but theoretically, that is a possibility. There's a question here. Will be at our quiz 3. I don't think I have done it, so I'm just gonna make it a quick one there. So just so we can. I thought I deployed that, but if not, I'm just gonna make a quick one, just so we can say that we did it. All right. Now, since we are on that question here, some of us were in class when I said that. Some of us were not. I'm just going to repeat this. Okay, officially, yes, by all means, I have to give you the evaluation here. Right? Unofficially, if I can say that, just don't say anything to anybody so the word doesn't get out. Right, really? I'm joking here. I'm extremely pleased with seeing your progress here in this class. I'm extremely pleased at your engagement in the topics to the point that as far as unofficially how I feel about evaluating you, I don't even feel the need to evaluate you because I can see that you're engaged on your own. You are not the cheating. It's not even in the dictionary of our class. Right? So I'm not worrying about any of the cheating or any kind of things that associated with that. I know that you want to grasp the concept of every little thing that we study, and you're doing this thing on your own, and you really, really want to know the stuff that is being served. Nobody has to watch you, which is awesome. All right. But officially, we have to deploy those tests so we can put the numbers with the marks, and that's what we're going to do. So yeah, so the that's why I'm doing those tests the way we do that. The other thing is that I wish we had a little bit more time in class, in person, so I could give you a proper, if you can say that, because what we're doing is also proper. Excuse me. I could give you a in-class test, but then in that case, I would have to design the questions slightly different. But I have no problem giving you this online test. It's just a formality for me. I can see your progress in person, and I'm more than satisfied with your engagement in this thing. So I have no problem. All of you, okay. Once you go out to the world, please do feel free to tell everybody that you know me. Okay. All right. So that's as far as that question that was in the chat line here. All right. Cool. All right. So next, so let's move to the next slide right here. Now, PCM, pulse code modulation, and coding. Right? What is encoding? Encoding is basically assigning a number to every little sample. So if we look at this thing here, that little point right here is going to be assigned a number. And that little point is going to be assigned a number. And that little point is going to be assigned a number. And those numbers are going to be shot into the pipes. And they're going to be deployed into the, well, transmitting medium, whatever that is, copper, air, or fiber, at a certain speed. So the listening device just has to adjust its speed to the listening intervals in order to get those numbers. So how often those numbers are going to be transmitted, and they will have to be received at the same baud rate, okay? Then that's going to decide about the resolution horizontally, sampling rate. And what's the bit depth? Bit depth is going to determine how finely we're going to chop those things vertically. What is going to be the smallest difference that we're going to notice? Also, that has to do with how much of something that's called digital noise is going to be introduced to the signal, and we'll talk about that, right? So let's say for the 8-bit sampling rate at different rates. So we have an 8-bit vertically. What does that 8-bit tell us? It's telling us how many samples we can have vertically. Yeah. Oops. So here we 8-bit of signal with 8-bit bit rate. We have 8 kilohertz sampling rate, which is going to give us 8,000 samples in 1 second. 8 kilohertz. 8,000 things happening per second. So that's going to give us 8 kilohertz sampling rate. Within 1 hertz. Within 1 second, we're going to have 8,000 samples. Quantized number string in decimal numbers. See, if you have 8 bits, all right? Hold on here. 8 bits, all right? Now, this is just a formality here. 2 to the 8. That's going to give us 256 samples, right? We knew that, right? And this would be the string that would be string of numbers converted to decimals, but of course, the string of numbers would be ones and zeros. So you would see like 1110 8-bit words. Now, sometimes you're going to have the signal chopped in 256 all vertically, and the midpoint is going to be 128. So anything above number 128 is going to be the positive value of the positive cycle. Anything that is less than 128 in decimal is going to represent the negative side of the cycle. Sometimes also, and we'll talk about that, we're going to designate the highest significant bit to be either 0 or 1, and you're going to get that from that 0, you're going to use the 7-bit to represent the 7 bits to represent the positive cycle, and another 7 bits to represent the negative cycle. And depending on the highest significant bit is going to be 1. That means, and followed by a number, is going to be the positive cycle, and or 0 followed by a number, that's going to be the negative cycle. Either way, you get the same resolution. You get the same thing. Now, quantized, okay, so 8 kilohertz will give you 8,000 samples. 16 kilohertz sampling rate is going to give you 16,000 samples per 1 second. And for 8 bits, the interval between the samples, you're going to have 125 microseconds. And of course, when it comes to 16,000 or 16 kilohertz sampling rate, the interval between the samples, time-wise, is going to be 62.5 microseconds. And let's see that 44.1 kilohertz, which is the CD quality sound. I didn't put the string because this is just so you can see. The interval between the samples is going to be approximately 22.68 microseconds. That's pretty good for our human ears. Right? Then comes the question of the aliasing. What did I write here? When a signal is sampled too slowly, the high frequencies get misinterpreted as lower frequencies. And that may result in a distorted wave shape when reconstructed. So that's because of aliasing. I put that thing in the black text. And now let's see when I have some grayed out text. Nyquist rate, so that's the minimum sampling frequency is twice the frequency. That's the minimum frequency in order to capture all the information in a band limited signal, which means we're, let's say, from 20 to 20 kilohertz, that would be limited by the band, right? Of 20 to 20 kilohertz. All right, so that's just a thing that we already know. Now, practical sampling, when it comes to certain signals, instead of sampling it with twice as the highest frequency, the real world systems use higher rates, for example, 5 times or 10 times, with anti-aliasing filters, which would be low-pass filters, to smoothly transition the unwanted frequencies, preventing spectral overlap. Whoa. Yeah. And ensuring accurate reconstruction. In summary, while the theorem says at least twice the sampling, 2 times, sampling at 10 times the highest frequency ensures adequate buffer for imperfect filters and captures enough data points per cycle to faithfully reproduce the waveform nuances, making the reconstruction process much more reliable and accurate. All right, so we mentioned something that's called low-pass filter. And the question would be, of course, how does a low-pass filter help with anti-aliasing? I'll tell you. Low-pass filter prevents aliasing by removing high-frequency components from the signal. Well, that's what low-pass filter does, right? Before the signal is sampled or digitized. That ensuring the frequencies above the half the sampling rate, which is the Nyquist frequency, the higher frequencies are eliminated. So there's basically less confusion of what things should be. Because if you have more higher frequencies, other frequencies combined with other higher frequencies, create something that called frequency beat and all that stuff. And sometimes that the aliasing can be a problem in audio, creating some weird sounds that don't exist in the original signal, and also in graphics as well. And I'll show you the next slide. Because yeah, graphics aliasing is also pretty good to kind of show what aliasing is. Basically, showing things that are not there. All right. So all the frequencies that are higher, which stops them from incorrectly appearing as lower frequencies, because lower frequencies would be a beat combined from many other frequencies present at the same time. So that's maintaining the signal integrity and preventing jagged edges or false patterns, and in images, so the graphics, and in audio. And when you download this thing, say, want to know more? Click here. Or you want to click here. You'll know even more. So as far as aliasing, I'm not sure how your monitor is reconstructing these three images on your screen. But if we look at the close-up uh, of the checkerboard that is basically here, now you can see some of the rugged edges are presented, and these should be straight. In reality, these are straight, just like that. But when you start looking further and further, then the analyzing element is getting confused by things are being further, which means we are seeing them too close together, and the analyzing elements are getting confused, and they're displaying some weird stuff that doesn't exist. So that's aliasing. Now, so this one here is no anti-aliasing, no anti-aliasing. Edges have jagged lines or jaggy lines. Now, some anti-aliasing. Things are looking a little bit better already, because that's eliminating the higher frequencies. And still, when you go further along, we're getting a little bit kind of grayed out area. It looks different than no aliasing. That's closer to the depth of field that we have with our human eyes, which means whatever we focus on, we see clearly, and whatever we are not focusing on, they're going to see, hazy. Okay. Now, more anti-aliasing. Edges look smoother still, right? You could see here and compare those. And of course, as you go further along, no matter what you do, sometimes the aliasing is still going to occur. But you can see the difference between more anti-aliasing filtering. It's still trying here, still trying to reconstruct things properly. And if we go further along, those squares appear closer together. So, which means with higher frequency. In photography, also, you can see some weird colors appearing, that color edges, and things like that. But if you translate that type of idea into audio, instead of seeing things that are not there, you're going to be hearing things that are not there. All right. Now, quantization. What do we mean by the word quantization here? Quantization is converting a continuous range of analog sample values into a finite, not as opposed to infinite, discrete or specific set of digital values. Like these. You can assign a number to every single little sample that you get. Gets assigned a number, and that number means something. Now, of course, these are, as I said, decimal representation of the binary numbers. Binary. All right, so let's go to quantization. In PCM, the analog signal must first be sampled, which means turned into discrete time pulses. And quantization is the second step. The amplitude of each sample is digitized. Each measurement is assigned a discrete numerical binary value. And that we also call that encoding. Over here, we have a sine wave that is being sampled. So here is the frequency of the sampling. Here is the granularity of the vertical representation of how fine we chop this thing vertically. Oops. And how fine we chop this thing horizontally. And every little point here or here gets a value that has the information on how high this thing went or how high we saw the signal at that particular moment and when we heard that, so it can be reconstructed. And these are the sort of like a visual representation of number being assigned to every level of amplitude and every time-based spot within the cycle that being or the waveform, because the sampling might not care about the cycle of the waveform. It just looks at it, takes a snapshot, and whatever he sees there, turns it into a number and sends it down the pipes. And then again it looks, and then again it looks. It doesn't matter what this is, how quick, how often we want to look at it and take a sample and shoot it down the pipes, so to speak. It doesn't matter on the frequency of this. We just have that, so we could have something to sample. But of course, when it comes to music, it looks nothing like this. It looks like many of those at different frequencies. So, with quantization resulting at this using 16 quantizing steps. Look, from 0 to 15. Right. So this will be something that's called, well, you can consider this thing as unsigned, right? Unsigned, which means not signed, like a signature, unsigned type of a transmission, as opposed to a signed transmission. Unsigned doesn't have plus or minus sign. We are measuring this thing from here to here, from the lowest to the highest. And signed would be assigning a sign, positive or negative sign. As I said, we're designating the highest significant bit to say that whatever the value of the other 7 bits are saying, they will give you the absolute value, and the highest significant bit is going to say, okay, mark it on this side or on that side of the 0 axis here, x-axis. Either way, when you're measuring from here to here, and don't give a signature to the level, because it's going to, this is your 0, or you're measuring from the middle and assigning here negative sign or positive sign, you end up with the same amount of bit depth. Because over here you have the whole thing, and you're presenting the thing from 0 to the whole thing, and you're dividing this thing into 2 halves of the whole thing. Right? But you still get the 2 halves of the whole thing, which means you get the whole thing. Right? Questions here. How many bits were used in this uniform quantization? What does mean it's uniform quantization? It means that all the steps are equal to each other. Ununiform quantization would be smaller sizes, smaller changes would be assigned more samples going that way. So we could have we could see the smallest changes better. And if changes are bigger, then you are not sampling things as often as far as the vertical bit depth is. But just not to make things confusing, we're going to say uniform. So how many bits were used? Well, 1, 2, 3, 4, 5, 15, which means 16 intervals here, right? Going vertically. 2 to what gives you 16? How many bits? How many bits the 0, 0, 1, 0, 0 would be represented with? 2 to what power gives you 16? I'll leave that with you, okay? All right. What's uniform quantization? Pros and cons. Uniform quantization is basically when you have a high level of changes, then uniform is pretty good, easier to accomplish, and it's going to give you the sample rates as far as vertically sampling. It's the error is going to be small. But if you have some signal that contains also some smaller changes, then you need to have, then the uniform thing is going to take it, put it through the same size of, I use the word pipe today a lot, which means some of the smaller changes might not be as noticed as they should be. Uniform quantization as opposed to what? Okay, what are the alternatives? Okay, I'll let you dig into that as well. And here's some of the reference here that I found. It's pretty cool, actually. I got that picture from that. All right, here, pulse code modulation, quantization and quantization, error and noise. As we know, quantization is converting a continuous range of analog sample values into finite discrete numbers. So we know that already. In PCM, the analog signal must be first sampled, turned into discrete pulses, and then it has to be quantized, which means the amplitude has to be assigned. So if you move along, stop here and take a look where it is. Write it down. And stop here and write down what you have. And stop here and write. So that's the frequency. And over here, write down what we have. Is going to be whenever you are sampling. So between this point and that point, we have that much to cover. So the number is going to be assigned to this value at this point, or that value as far as y-axis at this point here. And how far you're actually, what your resolution vertically is, that's going to be pulled to the closest value that you have as far as the vertical granularity. And this way, that's how we come up with errors, because whenever you are between those two sample points, that sample has to be assigned somewhere, and it's going to be pulled towards this if it's closer to that point, or it's going to be pulled towards that value if it's closer to that value on the y-axis. All right. So what do we have here? Example of 8-bit unsigned. See, unsigned PCM. What does that mean? Again, we're measuring from 0 to the highest. So this is our range of measurement. This is our lowest number. This is going to be our highest number. As opposed to signed, this is our reference number, and we are giving an absolute value of whatever it is, and the highest significant bit in that digital word is going to tell us whether you're going to put it here or here, that far where? Here or that far this way? So that's unsigned format. The amplitude values range from 0 to 255. Well, 256 actually, right? Well, it's 256 samples because 0 is actually something in digital world, right? The midpoint is going to be 128 or 0 to 80 in hexadecimal. Well, 0 to 80, 0 to 80 in hexadecimal represents a silence. This would be the silence. This would be non-silence. Represent the sign crossing, zero crossing point of the original. Okay. Value is above 128. So we talked about that already. Above 128 are positive. And values less than 128 is going to be negative. And this is unsigned. For the signed, we're going to have to go 128 this way and 128 that way. So we're going to have 60. Oh, is it plus 60 or minus 60? Look at the most significant bit. All right, dynamic range, 8-bit versus 16-bit. See here? More or less, this is what 8-bit looks like. No, don't pay attention to the waveform cycle because it doesn't matter. The sample rate does not depend on the cycle of the waveform. It's a pretty cool site here. If you want to log on to it, once you download it, you can actually choose the rate or the dynamic range. And it's going to give you, I just took some snapshots on that. But do not try to count the samples per cycle because it's not going to happen. It's not going to give you, so don't get confused. It's like, okay, so we have to chop it into 16 and here's a full cycle. Why am I not getting, no, it's just how often we look at whatever we have, and this is whatever we have. And in this case, seems to be a sine wave, but it could be completely something else. It's just how quick we are looking at this thing, how often we're looking to sample, right? So 8-bit, you see, it gives us okay type of reconstruction if you connect the dots. But 16-bit, it gives you just twice as many samples. So the dynamic range, you get from here to here. And yes, of course, you're going to get some error happening, but the error is going to be smaller. How much smaller? The error is going to be half, because whenever you are getting the maximum error that you can get is going to be plus or minus the half step of where you are. So when you stop to sample, and you're going to get some level. Now, is this thing closer to this, or is it closer to that? And that's the number it's going to get, which is going to create some sort of error happening, because if you look at the analog, you have infinite number of points between this point and that point, and also have infinite number of points between this point and that point, and so on. But when digital, You don't have the infinite number of points. And someone might say, uh, wow, so is digital or analog should be better, right? Because you have infinite. Well, that depends on the equipment that you have. How well the equipment can reconstruct what you're, that depends on the type of a coil you're going to use or the components, what is going to be the capacitive and inductive coupling between plus and minus on the cable that is coming. So just because the signal in analog ideally has infinite number of points here doesn't mean that even the analog equipment is going to give you a true representation. So that's why sometimes the digital systems might sound a little bit better. Well, better as far as the quality of the sound being represented instead of equipment, instead of representing the sound, representing, they would be presenting sounds of their own. So yes, we are limited by the physical reality of things, even with the analog equipment. But when it comes to increasing the number of bits, and just so you know, the number of bits, the bit dynamic range of the bits tells us how many levels we could see vertically. Here's one level, here's another level, here's another level. How so that the bit rate that gives us. The sampling rate is giving us the time of how often we stop and take a look and sample. So bit rate gives us the granularity this way, and sampling rate gives us the granularity this way. All right, improving resolution. This is the slide from the previous lecture. I just copied that so we could analyze it again a little bit. We can improve the resolution by increasing the number of quantization levels. However, another approach can be shown. So improving the resolution of the signal, we could improve the sampling going horizontally, or we could improve the sampling going vertically. If you improve it one way, horizontally, take more samples, you're going to get better representation of the signal if you do just that alone. Or if you improve vertically here, you also may get a better representation of what's coming in reality. However, in order to get the proper signal, you should have a pretty good chopping rate horizontally and pretty good chopping rate vertically. Then you can get a proper signal. So the dynamic range here, here's the terminology, dynamic range. Dynamic range of PCM is set by the maximum change, the maximum swing of the voltage vertically to the minimum change that we want to notice or that we are able to notice. And that also translates to the 2 to the power of the bit rate. How many bits? All right, so now we have 3 bits as a bit rate. We have a binary coded decimal, well, 3 bits only. So of course the other one was going to be 0. So just represented with 3 bits. 3 bits. 2 to the third, okay, gives you 8. 1, 2, a 3, a 4, a 5, 6, 7, 8. So the dynamic range is 8 with 3 bits. which means we can chop this whole signal from the weakest to the strongest. We can chop it into 8 bits if it's unsigned sampling. And of course, remember, if we was signed, then we would chop it into 4 this way and 4 that way. Either way, we get 8 in total, right? And there's some formulas here in decibels. Here's that. So it will be the dynamic range in decibels will be 20 log because we're dealing with voltages. So the ratio between the maximum change to the minimum change that we are able to notice within the signal. All right. And since V max over V min here equals 2 to the n, so we could just substitute that here. And we got nice and simple formula here. The dynamic range in decibels equals 20 log of 2 to the whatever number of bits that you have here. And over here, from this point to that point, what do we have? We have the same amount of bit rate on this picture. We have the same amount of bit depth here. So the bit number of bits didn't change. We have just changed how often we stop and take a look. So the sample rate has doubled. So of course, we're going to have a better representation because we're taking a look at what we have there more often. Whoa. Right. Again, there's another formula here. I'm going to say the dynamic range is going to be about, well, 6, because 6 is the, has to do with the 20 log. I'm not going to go into deriving that. So the dynamic range is 6.02 or just 6, which is half the voltage of whatever we have, because we go half this way and half that way. Divided by the by the number of bits times the number of bits. Decibels per bit, okay. Times the n, or 6.2, 6.02, or 6 times the number of bits. That's going to give us the dynamic range. So that comes to numbers. This is a unit. 6.02 decibels per bit times the number of bits. That's how you should read this. Or 6.02 times the number of bits. That's just dropping the unit here. And that's going to give us the bit rate in dBs. So here's the quantization error. What's quantization? It's assigning the level. This error is unavoidable of anything that has to do with PCM. But don't panic, it's not that bad, because the technology has gone so far that we can see so fine and sample so finely that we will never notice as humans. All right, so I say this error is unavoidable part of the PCM systems, pulse code modulation, arising because of continuous continuous range of amplitude values that must be represented by a finite, which is not infinite, but finite set of discrete or exact quantization levels, going up and down. The error is mathematically defined as the difference between the actual input value and its quantized output value. Again, the error, quantization error, is mathematically defined as the difference between the actual input, not the highest, sorry, the actual value and whatever the number represents, and tell us where to put the dot on the map, on the graph. Quantization noise. Well, quantization error is often modeled as random noise, not as quantization noise or quantization distortion, which raises the overall noise floor level. Noise floor of the signal. Noise floor, we are going to have some noise already because we are dealing with physical equipment. All the components, parts, and interference, whatever, we can't avoid that. It's going to be there. Some noise level is going to be, depending on how high quality equipment we're using. Add the quantization error, it's going to make that noise floor a little bit higher. Bounded error in a uniform quantizer. Remember what uniform quantizer is? Uniform quantization is all the steps are equal to each other when it comes to vertically. In ununiform, the smallest changes have more finer chopping, because just so we could see the smallest amount of changes. So of course, it makes sense to have finer magnifying glass here. And as we go to the bigger changes, percentage-wise, if we chop things vertically not as fine as we have bigger changes, we still get the same percentage error, or we still get acceptable percentage of an error. So that's an ununiform. But again, we're talking about uniform quantizer, where all the step size delta. The delta stands for the interval between top and bottom of this change that we're noticing. The maximum error is bounded and falls within the range of halfway of the delta, which is half of the step size. Let's see, right here. This is our delta from here to here. This is our change. And we're going to catch that change at either point of wherever this thing occurs. So the error means that the signal, when it's being captured at the moment that it occurs, is it closer to this point vertically, or is it closer to that point vertically? And that's going to get a signed number, none in between. So the quantization error, bound error, that we have the maximum error, is going to be plus or minus half size. Makes sense. Where do we get delta from? Well, it's the resolution. It's the smallest step interval, quantile interval per bit. And of course, in a uniform quantization, when it comes to dealing with the whole thing. And in ununiform quantization, you just have to consider the region you're looking at. The region of the smallest changes or the region of the bigger changes. Right? So the resolution is the Q. Number of bits, full size scale. Resolution is the Vmax, maximum change that we're noticing in the whole signal. Divided by the 2, the bit rate, 2 to the, so this is how many, this is 2 to the n, tells us how many equal parts we're going to have. So if you have 3 bits, it's going to be 2 to the, it's going to be divided by 8 different. So that's our resolution. All right, PCM postcode modulation signal to noise ratio. We're familiar with that already. But in digital, we have SQ&R, which means signal to quantization noise ratio. Because, right here, when we are capturing the point right at this point, we're going to assign it this value, not that value, because we just are not going to do that, because that's not the grainage that we're looking through. We're going to either get this or that. And if it's closer to that, we're going to have it here, which is okay for the resolution that we're going to accept. But this is not this, which means sorry, don't get dizzy. That inaccuracy of representing the signal is going to create noise. Noise is basically garbage, but it's still there. It's not how much noise we're willing to accept. The performance of PCMs are primarily measured by SQ&R, signal to quantization noise ratio. The performance of the PCM system is primarily measured by that type of signal to noise ratio. SQ&R is the ratio of the signal power to the quantization noise power. Because that noise that is going to be created because of inaccurate presentation, it's going to have some power too, typically expressed in decibels. For ideal uniform PCM system, I'm not going to say what uniform is again. Using the n number of bits for encoding, the maximum theoretical SQ&R is calculated by using the following formula, assuming a full-scale sinusoidal input. So when you have this, basically when the volume is all the way up. Sinusoidal, well, it's not clipped, not overdriven. So the signal to noise ratio, here's the formula, all right? Get it, remember it, write it down. It's 6.02 times the number of bits plus 1.76. And of course, we're going to get this in dB. Here's the phone ringing. It's going to stop. Somebody pick it up, please. Okay, somebody picked it up. Good. The SQNR is directly and linearly proportional to the number of bits, which means the more bit depth we're going to have, talking vertically, right? The less errors we're going to have when it comes to representing the signal that we have to recreate. The less bits, the more inaccurate recreation of the signal is going to be, which is going to create more error, which is going to translate into more SQNR, signal to quantization noise ratio. There's a 6 dB rule for every one additional bit. So let's say you have 8-bit as opposed to 9-bit signal sampling vertically quantization. For every additional bit used in PCM system, the SQNR improves by approximately 6 decibels. Since 6.02 times 1 equals 6, right? Approximately 6. So 6 dB. Which basically, when it comes to voltage, because we're dealing with voltage, amplitude voltages, and we have difference of 6 dBs, we're halving it. You add one more bit to the sampling, the bit rate, you're cutting the noise in half, which means you're getting clearer sound. Couple of examples here. Increasing a system's resolution from 8-bit to 16 bits. Whoa, we're doubling the power of transmission here. Sorry, I shouldn't be saying that. I'm just paraphrasing things. All right, we're increasing the number of the system's resolution from 8 bits to 16 bits. Now, this is going to increase the signal to quantization noise ratio by approximately 48 decibels. Adding 1 bit gives us improvement of 6 decibels. Adding 8 bits, because from 8 to 16, we're adding 8 more bits. Simple formula. See the 6 dB rule? All right. So okay. So 8 times 6 dB per bit, decibels per bit, that gives us 48 decibels. Now, is that 48 decibels signal, overall signal to noise ratio? No, it is the improvement from having, if you are listening to 8-bit system and then you're listening to the same song in 16 bits, then you're going to have improvement of the noise reduction by 48 dBs. What type of noise? Digital noise reduction. How does that manifest itself to your ears? One, you're going to have a little bit more, noticeably clearer sound, more crisp. and the other, you're going to hear the sound in a little bit more muddy way. To the point that sometimes when you hear some of the, well, sometimes when you dial a support number, technical support number, and when they're really, really stretching the bandwidth, so they can either stretch the bandwidth or put more signal, more channels onto a pair of wires, so they could get more channels per less wires physically. They're going to push that to the limit. The extreme thing is that you're going to stop understanding what somebody is saying because of you're going to hear it like a garble, like a turkey kind of what is it? Turkey garble. At some points, or maybe all the time that you're going to, because when the voice is going through different type of circuitry, every circuit is going to add its own noise to the point that after the fifth one that the signal passes through, it's getting to be unrecognizable. And at some point, you can hear the phone call is on the other side. The person is quieter or even garbled to the point that you can't understand. So that's the difference between the digital noise. All right, so increasing from 8-bit to 6-bit depth gives us 48 dBs advantage, which means the noise is eliminated by 48 decibels. That's a lot. Get another example. That's the last slide. All right, the difference between 8-bit and 16-bit. If you apply that formula, so I didn't first, okay, so calculate the SQNR for an 8-bit system. Again, let's just say that it's a uniform quantizer that we are dealing with. So how many bits do we have in 8 bits? Well, let me think. I think it's 8. All right, let's put that 8. Let's take a risk, right? Apply the formula here, right? Plug in the numbers. Well, we only have one number to plug in. See how simple that one is? So SQNR, the signal to noise ratio, quantizing error noise ratio, 6.02 times the number of bits plus 1.76. And it comes up to about 49.92 decibels. So the noise level is 49 decibels lower than the maximum signal that is there. That's how we should understand that. That's the signal to noise ratio. Well, for 16 bits, all right? How are we going to have better signal to noise? Of course, we're going to have better signal. How much? Okay. For 16 bits, using the same process, we get the SQNR of 98. So that's even better. The noise level is 98. That's a lot of dBs lower than the full swing of the signal. And if we get take that and subtract that number, well, we're going to get the improvement between 16 and 8-bit, which is about 48 bits. Sorry, 48.16 dBs, which is that answer to the previous tricky, eh? Cool. All right. Let me see here. There we are. So this is, I got some assignments to mark. I think we still have 11 participants here, so we are good. I don't have to repeat the test thingy. I'm going to be in the lab room if anybody needs to brush up on anything, any kind of undone labs. So I will be in the lab rooms, and I'm also going to be there at the last in-person class. If anybody wants to talk about anything that has to do with the course and stuff like that. All right. Um, so I'll be present during the lab times and the last lecture time that is planned there. It was a pleasure to work with every single one of you, and I hope to see you again at some point. And this is Mr. Bach signing out. Thank you, thank you, thank you, thank you. I'll be here till Thursday, no, actually till Friday. May I speak with you before we go? Yes, you may. Um, but let me just turn off the recording here. Was it Sean? Okay. Do you want Sean? Do you want to speak privately? Okay. So I'm going to hold on, Sean. Where are you? I'm going to send you. I'm going to establish another Zoom session. Okay, and I'll send you the. Give me your last name. Just type the last name so I don't have to search for it in the student list. Did I stop recording already? Oh, yeah, I got to stop recording. Okay. Thank you, guys and gals. I'll see you later.